Here's a titration problem where we're asked to consider a strong acid being added to a weak base solution. The problem that we had worked out in class was a strong base added to a weak acid, which is a little bit like the opposite. Let's start with the easiest part of this problem, which is part A, wherein 0 milliliters of the strong acid nitric acid has been added. In this case, it's just a weak base problem, just like we had done in chapter 14. We'll write a base dissociation equation, and we'll set up an ice table showing how the weak base protonates and produces hydroxide in the process. Anytime you have liquid water in an ice table, it drops out. And we'll work out this problem in units of molarity, whereas with reaction to completion tables, we have to work them out in units of number of moles. So initially we have no hydroxide and none of the conjugate acid of the weak base. So zeros under those. I should have written M for molarity here. We'll shift to the side with the zeros, so we end up with X and 0.1 minus X. When we write the equilibrium expression, we get X squared over the quantity 0.1 minus X. We'll go ahead and make the mathematical assumption that 0.1 minus X is roughly 0.1. And we'll set that equal to the Kb value that they gave us at the beginning of the problem, 3 times 10 to the negative 6. Solving for x, we arrive at 5.5 times 10 to the negative 4th. And in this ice table, x is the equilibrium hydroxide concentration. So when we go to calculate POH, we just take negative log of the value of x, and that works out to be 3.26. Since they're asking for pH and not POH, we'll just subtract from 14. And it works out to be 10.74. Okay, we've got the answer to part A. That one wasn't too hard, or not intended to be too hard, or at least I'd say it's not the new part. When we get to part B and following parts of this problem, that's where we have to consider the presence of a strong species. So let's draw a picture of the reaction vessel and write down everything that's in it. In this problem, we have the weak base H2NNH2. To that, we're adding some nitric acid. Since nitric acid is a strong acid, it exists as broken apart H plus ions and nitrate ions. And so when I write nitric acid, I'm writing them as split apart ions. Lastly, as with any aqueous solution, we have water. The presence of hydrogen means that we're going to have a reaction to completion. If you ever have hydrogen or hydroxide in the reaction vessel, before you can consider any equilibria, you've got to consider the reaction to completion of the strong species. In this case, it's a strong acid species that will react with the best base available to it. Considering the other species in the reaction vessel, we have the conjugate base of a strong acid, which is itself a very weak base, a base that will not be important in determining pH. We have a base whose K value they gave us is 3 times 10 to the negative 6, and we have water, which you can always think of as a potential acid or base, whose K value is 10 to the negative 14th. between the two choices of bases, we have something whose K value is much bigger than water. That is going to be the base with which hydrogen reacts to completion. So we have hydrogen and H2NNH2 reacting to become, what happens in the reaction to completion is just the proton tacks onto the base. By definition, bases are substances that receive hydrogen ions. We're going to make a before and after table to show the reaction to completion. And when we work out that before and after table, we'll note the numbers of moles, not the concentration in molarity. If you read the problem carefully, it says that in the original solution there was 100 milliliters of 0.1 molar H2NNH2. Multiplying the volume in liters by the molarity, we get 0.01 moles of the base. And if you look at your drawing of the reaction vessel, there is no conjugate acid of the strong base initially. This setup, a reaction to completion with this equation, with 0.01 moles of the weak base and 0 moles of H2NNH3, the conjugate acid, will be the same for parts B, C, D, E, and F of this problem. So it's going to be all the same for this setup. The thing that will change is going to be the initial number of moles of hydrogen ions, because you'll have added different numbers of milliliters with each different part of the problem. In part B, we've added 20 milliliters of nitric acid. 20 milliliters times a concentration that they tell us at the beginning of the problem of 0.2 molar. If you convert 20 milliliters into 0.02 liters and then multiply that by 0.2, you arrive at 0.004 moles. So for this reaction to completion table, it's 0.004 moles of hydrogen initially. In any reaction to completion table, one of the reactants reacts completely away down to 0. And when we consider that reduction of 0.004 for the hydrogen, we'll also have a reduction of 0.004 moles for the weak base. So instead of 0.01, now it's 0.006. And on the opposite side of the equation, we'll see an increase of 0.004 to bring that number of moles up to 0.004. Now we've completed our reaction to completion table. And at the end of it, we have some weak base, and we have some leftover conjugate acid of that weak base. As long as you have at least some weak base and some of its conjugate acid, you get to use the Henderson-Hasselbalch equation in order to find the pH of the solution. They didn't give us a Ka value initially. Instead, they gave us the Kb value of H2NNH2. That's no matter. We can find the Ka value from Kw and divide the Kb by Kw. Or I'm sorry, divide Kw by Kb. So 1 times 10 to the negative 14th over 3 times 10 to the negative 6th would be the Ka value. And then we'll take our, for the rest of the equation, our numbers of moles of base and acid, because don't worry that the number of moles is different from the molarity. you can still just plug in those numbers and solve. So we'll take the base number 0.006 divided by the acid number 0.004. And when we crunch those numbers, we arrive at 8.65 for the pH. That setup that we showed in part B is going to be repeated throughout the rest of this problem. Let's move on to part C. In part C, we've added 25 milliliters of the strong acid. We'll set up the reaction to completion just like we had in part B. And the initial number of moles of the weak base is the same as before, 0.01, and the conjugate acid of that base, 0. The thing that will change is the number of moles of hydrogen. At this point, we've added 25 milliliters, and the concentration of the nitric acid was 0.2 molar. So if we take 0.025 liters times 0.2 molar, we get 0.005 moles. That's the initial number of moles of the hydrogen. One of the two reactants goes all the way down to 0. It's the one with fewer moles. 0.005 is less than 0.01. Notice that there's the same reduction in amount for both reactants. And on the product side of the equation, it's an increase of that same amount to give us 0.005. Here's an interesting situation. We've got equal numbers of moles of both the weak acid and its conjugate base after the reaction to completion. This is the halfway point of the titration. We can still use Henderson-Hasselbalch here. But as we'll see, the pH is going to work out to be the pKa of the acid. Just like before, find Ka from Kw and Kb. And just plug in numbers of moles instead of molarity. Don't worry, because the ratio of moles is also the ratio of the molarity. The log of 1 is 0. So we get a pH in part C of 8.48. Notice that the pH is going down as we continue in this problem because we're adding an acid to a base. But it'll go down by differing amounts each time. Part D, we have added 40 milliliters of the strong acid. Same setup as before. The proton tacks onto the weak base to give us H2NNH3. And just like before, the initial number of moles of the base and the conjugate acid are the same as the previous reactions to completion. The thing that will be different is the number of moles of hydrogen ion. This time we've got 40 milliliters, which is 0.04 liters, times 0.2, and we get 0.008 moles. One of the reactants goes all the way down to 0, and it's the one that has fewer moles initially. The reduction in number of moles is the same. On the product side of the equation, it's not a reduction but an increase in the number of moles by that same amount, 0.008. At the end of this reaction to completion, we still have at least some weak base and some of its conjugate acid. So we can still use Henderson-Hasselbalch. things are going to get different in part E. Henderson-Hasselbalch will no longer apply. Base over acid would be 0.002 over 0.008. And the pH works out to be 7.87, which again is a reduction from what we previously had. On to part E. The only difference in part E as compared to the initial setups before is that we have a different initial number of moles of hydrogen. 50 milliliters of 0.2 molar hydrogen ions would be 0.05 times 0.2 gives us 0.01. Notice that in part E, we have the same number of moles of both the acid and the base. That means we're at the equivalence point. At the end of the reaction to completion, we'll have reacted away all of hydrogen and H2NNH2. On the right side of the equation, it's an increase of H2NNH3. Here, we don't have any weak base left. We don't have any strong acid. The only thing we have left over is some of the conjugate acid of the weak base. So we cannot use Henderson-Hasselbalch. We'll ice it down. In our ice table, we'll consider that we have 0.01 moles of the conjugate acid of a weak base, which means it's a weak acid. We'll write an acid dissociation equation. Acids, by definition, kick off a proton. And you'll produce some of the weak base, but not very much, as we'll see. Ice tables are worked out in units of molarity, not numbers of moles. So to get the molarity, we're going to take the 0.01 moles of the weak acid we had at the end of the reaction to completion, and we're going to divide it by the total volume at that point. If you read the problem carefully, we started with 100 milliliters of the weak acid, and to that we added 50 milliliters of the 100 milliliters of the weak base, and we added 50 milliliters of the strong acid. The total volume then, if you add 50 milliliters to 100 milliliters, would be 150 milliliters. In liters, that's 0.15. When we divide this out, we get 0.067 molar. And at the end of the reaction to completion, we didn't have any leftover H plus or H2NNH2. Back to what you know from chapter 14, shift to the side with the zeros. We'll make a nice ice table. And we'll write a Ka expression. we'll go ahead and make the mathematical assumption that 0.067 minus x is roughly 0.067. They didn't give us a Ka value. They gave us the Kb of its conjugate, so we'll just find that Ka value from Kw by taking Kw over Kb. In this case, x works out to be 1.5 times 10 to the negative fifth. And in this ice table, hydrogen ion is the value of x at equilibrium. So to get pH, we just take negative log of that number. And we get a pH of 4.83. That was the toughest part of this problem. Now for the last one, which is going to be easier, I guarantee you. Part F, we'll start out the same way as before. We'll tack on a proton to make H2NNH3. The only thing that's going to be different this time is we've got 100 milliliters of the strong acid added. 100 milliliters or 0.1 liters times 0.2 molar gives us an initial number of moles of 0.02. Here, the initial number of moles of the strong acid is bigger than the initial number of moles of the weak base. So it's the weak base that goes down to 0 in the reaction to completion table. And the strong acid is left with 0.01. The same reduction is seen by both reactants. Both go down by 0.01. And on the product side, it's an increase of 0.01. But here, at the end of the reaction to completion, we have leftover hydrogen ions, which is a strong species. If you have leftover strong species, that is going to be what governs the pH, not the leftover weak species. Yes, the weak acid will contribute some hydrogen, but not nearly as much as what the strong acid will contribute. So to get pH, all we need to do is take the negative log of the hydrogen concentration as contributed by the strong acid. We'll take the 0.01 moles and divide it by the total volume at this point. In part F, we've added 100 milliliters to an already pre-existing 100 milliliters of the weak base. So 100 mils of the acid added to 100 mils of the base gives you 200 mils, or 0.2 liters. And when you divide that, we get 0.05 molar, and taking the pH, we get 1.3. So there was a lot of calculation in this problem. Let's summarize. If we consider the volume of nitric acid added and the pH that we arrived at 0 milliliters of the strong acid, we had a pH of 10.74. 50 gave us a pH of 8.65. Oops, sorry, I got those numbers wrong. It was 20 milliliters that gave us 8.65. 25 milliliters gives us 8.48. 40 milliliters gives us 7.87. 50 milliliters gave us 4.83, and 100 milliliters gives us 1.30. You'll see that the pH changes unevenly. If we do a quick plot of this, pH against volume of acid, and you plotted pHs ranging from 0 up to 11, and volumes of acid added from 0 up to 100, we'd get a graph whose shape kind of looks like this, where the inflection point, the point where it changes from being curvy down to curvy up, is your equivalence point. We saw that at the pH of 50. Where the pH was 4.83 and the number of milliliters of base added was 50. The halfway point of the titration, that is where you've added half the amount of acid that would be required to neutralize the base, that was found at a pH of 8.48. At that point in the titration, the pH of the solution equals the pK, this time it's a pKb, of the weak base that we're titrating. If this were an acid being titrated by a strong base, it would be pH equals pKa. And then in the other points of the graph, we've got when 0 milliliters of acid, that's just this weak base solution itself. At 20 milliliters of acid added, that's approaching the halfway point, well into you're in the buffer zone where the pH changes are minimized, where you have at least some weak base and its conjugate acid. Then we have the halfway point at 25 milliliters. Then we're approaching the equivalence point at 40. We're at the equivalence point at 50, and we're beyond the equivalence point at 100 milliliters of base, where you have leftover hydrogen ions.